Okay, so I'm not sure I can monitor the chat continuously. So please, students who are attending online, if you have question, just make sure if I don't reply, you may try on the chat, but if I don't reply, please step in with the micro. Okay, and then I have to share my screen. Okay, here we are. Good. So we started to discuss what are the problems associated to climate change. We, first of all, define what is climate and what is weather. Keep in mind, these definitions are extremely important. So at your exam, you for sure will get some questions on the definitions of climate, weather. So we already introduced what is climate, what is weather, and what is the difference between change and variability. But keep in mind that we talk about climate, and of course, talking about climate, we also talk about climate change. But we have to get clear the definition of what is climate, what is change, and what is variability, which can be very similar to change in the practical effects. Okay. Of course, it's different, the solution. If something is due to variability, the solution is different with respect to something due to change. And it's different also the attribution, because a relevant problem with climate change is the attribution problem. So what is the reason for change? If the reason is internal variability, which may give rise to change, it's a different story from human-induced changes. And then we talked about the problems associated with climate change. We talked about floods, droughts, we talked about hurricanes, and I think the list is complete. Now let me talk. We started also talking about the benefits, and we already discussed this slide. It is important also to discuss the positive impacts of climate change, because if we want to find solutions, because this is our aim, our final aim, finding solutions, of course, we have to get a full picture of everything is associated to the problem, because the solution, of course, would eliminate the benefits. And we have to take into account then what are the benefits. In general, we believe that the benefits in economic terms and in social terms are negligible with respect to the negative impacts. This is true if you look at the global picture, but if you look to a particular country which is benefited, of course, in the local picture of that particular country, the benefit is larger than the negative impact. And we have to be well aware of the big picture. Big picture means global picture, but means also local pictures. We have to be aware because, of course, finding solutions needs to take into account any side effect of the solutions. Because keep in mind that any intervention, any medicine has a side effect. So we take medicines, and I'm looking at the students in medicine because, of course, we suppose that the benefits are larger than the side effects. But we have to be aware of the side effects. And there is one thing that we can learn from medicine. In medicine, before adopting a therapy and before accepting application of the therapy to the public, they make a lot of experiments, statistics, and really, there is a really rigorous approach to that. So before proposing a solution in medical science, they really want to have a clear picture of any side effect, any positive effect, with a very rigorous analysis. And in principle, we should adopt the same thing also when discussing solutions about climate change. And in particular, in medicine, what they do is statistical analysis of experiments, of results from experiments. Why? Because there is always uncertainty in any approach in anything that is associated to the human life, there is always uncertainty. And by making several experiments and the statistical assessment in medical science, they aim to get a knowledge of the uncertainty so that they know there is uncertainty. They know that it's unavoidable because any human body is an individual subject, but they try to take uncertainty under control. And we should do the same in climate science. So today, we believe that decarbonization is a good solution, but decarbonization has side effects, and in particular has a large social cost that is to be paid by people. And similarly to other very rigorous sciences, we should be fully aware of the side effects and the uncertainty associated to destination. In climate science, somebody says we cannot make experiments because we have only one planet, and therefore we cannot make an experiment. So we cannot think of closing the Gibraltar Passage and then see what happens to the temperature of the Mediterranean Sea or the sea level rise in the Mediterranean Sea. We cannot do that. But still, we have means in science, in any branch of science, to estimate uncertainty, to get uncertainty under control. This is what we should do. And this is why we should not be, in a way, we should not be against discussing also the benefits given by climate change. They are real, they are there, and we have to try to know everything. By the way, I cited medicine because I think it is a very good example of a science that is very rigorous before proposing a solution. And it's not only climate science that is less rigorous. There are several other branches of sciences where we are less rigorous in the homologation, in the acceptance of a solution, in the evaluation, assessment of a solution. And I mean, I think we should really take the example from the medical sciences because, of course, there is a different ethical implication in medical science because you are working directly on a body. And therefore, this rigor is to be, I mean, is suggested in order to comply with the ethical codes. But also when we talk about science, when we talk about floods, we are not working directly on a human body, but still the implication is loss of lives for many of these disasters. So we should really rely on a very rigorous approach when we provide the scientific basis for finding solutions. I made this discussion because I wanted to discuss with you this aspect because there is, in general, in the scientific community, a kind of resistance to talk about the benefits of climate change. Because, of course, the concern is that if we really want solutions, we shouldn't talk about benefits given by the problem, because it is believed that politicians and, in general, the social organization need warnings rather than a kind of reassurance. But on the other hand, if we want to focus on science, and if we are scientists, we have to take a rigorous approach. In communication, may be a different story. So I understand that the strategy in communication may be different depending on the target, depending on the context. But in science, I think we should stick on rigor. The purpose of science should be to describe the truth, to provide a true picture. And so benefits are a part of this true picture. Okay, let's move forward. Now, in order to get this better understanding of science, this better control of uncertainty, this organization of experiment, organization of knowledge, we are aware that we need a global effort. and therefore in the scientific community and also in the United Nations, it was made an effort to try to reach a convergence of the various researches that are done at global level on climate change. And the idea was to create an intergovernmental organization of the United Nations, which was tasked with the mission of improving our understanding of the climate system. And this panel is the Intergovernmental Panel on Climate Change, usually indicated with the acronym IPCC. It has been composed by I would say some hundreds of scientists working on the different disciplines that are part of climate science, including social sciences, communication, etc. Basically, the Intergovernmental Panel on Climate Change, and you have the link here on these slides, we can open it. And let me just see where it is. Or let me open it here. Okay, very good. On this website, you find a lot of information on the science of climate change, indeed. And in particular, you find the reports, the task, the IPCC is tasked with the job of producing periodic reports, and now they are producing the 6th report. IPCC was started, I think, in 2003, so about 22 years ago, and they published already 5 assessment reports. And if you click here, you see that there is a link on the 5th assessment report, a link to the 6th. I'm not sure if the 6th is already concluded, maybe. These reports provide a lot of information, a lot of data also, a lot of references, and they are definitely interesting. There are also synthesis reports and summaries for policymakers, which are quite easy to read. It's a useful source of information. Just to complete the information, basically, you may know that there is a huge debate ongoing in the scientific community about climate, and the recent events at the political level, at the geopolitical level, global events have reinforced this debate. You know, after Trump's election, you have heard about the orders that he's issuing, and these orders basically try to step back a little bit from the effort of United States towards decarbonization. Indeed, there is a debate also in the scientific community, and the debate is on the effectiveness as decarbonization as a solution. And therefore, you know, this debate is also extended to the scientific community. So you may have heard that the scientific community is unanimous on the opportunity to make a global effort and a very huge effort towards decarbonization. Actually, I couldn't say it's so unanimous. There is a majority of scientists that indeed are convinced that decarbonization is a good solution because the CO2 emissions they think are responsible for the changes in climate. But there is also a consistent part of the scientific community who is more inclined towards adaptation to climate change because they don't feel very comfortable with, especially with the timing of decarbonization and the time it takes to the climate system to react to carbon emissions. So I'm saying this because the Intergovernmental Panel on Climate Change, some people say that it's a bit biased towards the decarbonization and as a good solution. I would say that anyway, the work of the IPCC is really important work, and it's really good reference. So I am really in favor, and this is why I'm telling you, look at this website, because if you look on the web for information on climate change, you find so many references, and indeed some of them are rubbish. Then the Governmental Panel on Climate Change, this website, the information that you find here, definitely it's very, very good. It's a good information. And of course, you may think that there is a little bit of bias, but it's not a problem. I mean, because you have also the technical knowledge in order to understand yourself, to understand what is presented and to compare with the other interpretations. Okay, and just let me close this and let me go back here. So here you see a graph of the global temperature, but we already have seen one similar graph. This is provided by IPCC, actually. It's taken from the 6th assessment report. And this is basically changing global surface temperature and reconstructed by climate models. And here you see a comparison between two things. The reconstruction of global warming by climate models, it is the pink, yellow, pink, brown, light brown band, okay? What you see here, simulated, you see simulated human and natural. So what this means? It means that you see here the observed dark line change in temperature and the result from the simulation of climate models. And here in green, in light green, you see the same simulation without the human emissions of CO2. So the difference between these two bands is light brown is with human emissions of CO2, and the light green is without human emissions. So what we see here, we see that the only way to reproduce what has been observed is by including in the model simulation the CO2 emissions by humans. What is the purpose of this comparison? To show that the human emission of CO2 are indeed a fundamental driver of the change in temperature. Okay. Fine. And remember what we defined, what we discussed last week. For what reason we believe that climate change is human-induced? And the correct answer is because models cannot simulate the recent increase in temperature without human CO2 emissions. Okay. So basically, this comparison is saying a clear thing. It is saying that emissions are important. Emissions caused the global warming, and therefore the solution is decarbonization. So this figure is clearly in favor of decarbonization and explaining climate change as a human effect. Actually, this figure is the subject of debate in the scientific literature because some scientists do not agree with this interpretation. They say that there are sources of uncertainty that make these bands larger. So you see the two bands are well separated, well distinguished. So the brown band is well distinguished by the green band. Some people say yes, but if we consider additional sources of uncertainty, the size of the band would increase, and therefore they would become almost overlapping. I just try to give you an idea of what is the debate, because I think this debate is really important. Is it clear, my lecturing so far? Yeah, no questions? Okay. Okay, and remember one thing. The IPCC usually associates, and this is a very good practice, to any statement a levels of confidence. Maybe I have a figure, just 1 second. Next one. No, okay, let me just check the next, okay. I'll find you a figure. Anyway, for any statement, like presenting this picture here, they say, I am highly confident on the results, I have medium confidence, I have low confidence. How they estimate the confidence is also interesting. First of all, let me just say one more time. The fact that they are associating a level of confidence is very good, because this goes towards an assessment of uncertainty, which is what I advocated when I started this lecture. So it is very good that they say, okay, I think this graph is fine with high confidence. So try to identify, if you look at the IPCC report, the confidence associated with the statements. It's very important. But how they confirm, how they estimate the confidence, this is also important. They associate to any statement a score based on 2 things: evidence from data and consensus. So if they find good evidence from data supporting the statement and consensus between scientists very good, then they say high confidence. The problem is that sometimes they miss the data, because with climate we have this problem. We don't have an extended set of data, and therefore associating the confidence score associated to data may be difficult, and therefore when they miss data they shift more on consensus. And they have a table guiding data support and consensus, and they attribute a consensus, they attribute a score to the support by data, and then they come out with the statement: high confidence, low confidence, medium confidence, etc. Data support is very good. And this is what an engineer usually does. Engineers usually look at the data, and the support given by the data is extremely also resilient. I mean, it's solid, it's objective. As I said, the problem is that we don't have long data series. I'm not sure whether I already made this discussion last week, but it is a bit strange that humans didn't start observing weather and therefore climate until recently. It is a bit strange because they started observing the stars like 3,000 years ago, while they didn't observe the level of rivers, they didn't observe rainfall, which are very easy to measure. I mean, rainfall is extremely easy. You put just a tank outside, and every day you go there and you measure with a ruler. You measure the depth of water, and then you empty the tank, put the tank again there. It's extremely simple. But humans didn't start to measure rainfall until the first rainfall series measured regularly on daily basis. It's the rainfall series in Padua, Italy, 1725. So 300 years ago, precisely 300 years ago. Is nothing. But for climate, is nothing. For climate, for geology, 300 years is nothing. And probably people didn't observe weather or climate because they didn't need it. There are few exceptions, like the Egyptians. They needed to measure the Nile River level for obvious reasons, because irrigation dependent on, and also fertilization dependent on the Nile River, and therefore they, for 600 years, they observed the annual maximum of the Nile River. But this is an exception. So basically, the data support may be very small. And therefore they shift on consensus. Now, consensus in science, this is an interesting story, interesting discussion. Science shouldn't be based on consensus, and you may find several references in the literature, because science should be based on the truth, not on consensus. And many times when science relied on consensus, humans made tremendous mistakes. You may remember Galileo. He was forced to retract his scientific theories. And after 600 years, the Pope apologized with Galileo. You may know the story, because the church recognized that they were wrong. And they were forced by consensus. The consensus was that Galileo's theory was wrong. But Galileo was based on scientific investigation. And so it was a big mistake to force Galileo to retract his theory. And probably we would have gained a larger knowledge if the value of Galileo's theory was recognized earlier. So, I mean, relying on consensus in science is a bit dangerous. Consensus is perfect for democracy, for politics, for democratic elections. Of course, it's a matter of consensus, and should really rely on consensus, because democracy is based on consensus of people. But science shouldn't rely on consensus. So you understand the debate that is behind climate, the IPCC, and whatever. And I really would like to provide you, at the best of my knowledge and my capability, my capacity, an objective view of these debates. And there is one additional thing that I would like to emphasize, because it helps to get oriented in this big picture of climate change. We are talking so far about temperature. We discussed a little bit floods, droughts, but the only data that I showed you so far are related to temperature. Temperature is a nice variable. It's very nice. Why it's very nice, temperature? Because it has a low variability in time and space. You can understand this. If you think at the temperature variability in space, it's impossible that here in Bologna you have like 12 degrees, and you move to Florence and you find -40. It's impossible. The variability of temperature in space is small, and also the variability of temperature in time is small. You don't get from 0 degrees in Bologna, next day 30 degrees. It's impossible. You may experience large increases in temperature, but from 0 you can shift to 15, and it's already something really amazing, really astonishing. So this small variability in time and space makes temperature a nice, a friendly variable. It's relatively easy to predict temperature. Also, for those of you who have some background in statistics, temperature data are close to Gaussian, which means low variability again. And this is a statistical terminology, so don't worry if you don't understand, if you don't know the term Gaussian, it's not needed. But it says small variability. So being a temperature a friendly variable, it is relatively easy to model it. So climate models in reproducing temperature, indeed, they are quite fine. So this simulation here, you see that the uncertainty band is quite small around the data, encompassing the data, first of all, which means that the model is good, and the band is quite small, is quite thin, which means that also uncertainty is not relevant. And on the other hand, being the process relatively simple of temperature, modeling temperature is relatively simple, it is reasonable to assume that with the increase of CO2 emission, you have an increase in temperature. So it is fine. I mean, this result is not so debatable. The huge debate, indeed, is not around temperature. But there is a but, and the effect of climate change, yes, it is given by temperature as well, but it is more relevant for other variables, like rainfall. Floods and droughts are related to rainfall, not necessarily to temperature. Okay, droughts, a little bit more on temperature, but not much. If we had an increase in temperature, and also an increase in rainfall, we wouldn't have the drought problem. If we had an increase in temperature and rainfall streams didn't increase, we wouldn't have a flood problem. So it's not only temperature. The big question is the increase in temperature, which we are confident is due to, indeed, at least in part, to human emission, is this increase in temperature also implying an increase in flood and drought risk, so changes in rainfall? This is a big question. And uncertainty in this question is much larger than the uncertainty that we have in our understanding of temperature, because rainfall is highly variable. If you think of rainfall extremes, indeed, if you experience a big storm in summer here, maybe that you move for 200 meters and there is no storm. We all know this. Summer storms are very concentrated in space. There is a lot of variability in space and also a lot of variability in time. You may start a day, completely sunny day, until like noon, and then in half an hour you get the sky completely cloudy and then a big storm. There is a big variability in time. To describe these variables is much more difficult. It means that the phenomena associated, the underlying processes are highly heterogeneous in space, and in time, their evolution in time is characterized by a lot of energy. Big changes means a lot of energy and means probably turbulence. And turbulence is something that is really difficult to model. Anytime that you have to model turbulence, so processes that are really chaotic, like a lot of mess, it becomes more difficult. So the level of confidence that we have in the implication of climate change on rainfall and therefore floods and droughts, it's much lower. Our level of confidence is much lower. So the big question is not really whether global warming is there. It's there for sure. And it's not also a big question whether global warming is associated to human emission. For sure, at least in part it is. It is clear, at least in part it is. And then we may discuss what in part means. In part means that human emissions are the primary driver, or the primary driver of global warming is something different. But still, human emissions are part of it. This is not the big question. The big question is, but this global warming, these human emissions, are causing really an increase in floods and drought risk? And if yes, where? Under which conditions? Because, of course, high variability in space means that in one place could be nothing. So the implication of human emissions, global warming on flood risk is zero. In another place, given that there is spatial variability, the implication can be really dramatic. And for sure it is in some places. It's clear that, for instance, if you think of water resources availability, association between water resources availability and global warming, I said earlier, droughts are related to rainfall. This is only partly true. Let me say something more. A drought can also be caused by lack of snowmelt. So not only rainfall, but snowfall months earlier, and then snowmelt some months earlier. If you have global warming and anticipated snowmelt, then you may get in the dry season where you don't have any more snow to melt. And therefore, this is a case where global warming may have an influence on water resources, because it does, even if it doesn't have an influence on precipitation, it has an influence on the dynamics of snowmelt. So this is a clear example that in one place you may have an implication in drought risk of global warming, of climate change. In another place, nothing. So these are the big questions. The big questions. And if you look at the capability of climate models to reproduce what has been observed here, you see fine. I mean, the yellow band is around the observed data. But if you make a similar graph for past rainfall, situation is not so good because uncertainty is larger. Any question? Okay, let me see if I can eliminate this. Okay. Now, on the other hand, water-related disasters are the most impactful climate-related events. So, I said temperature is easier. Fine. Water is not as easy, but unfortunately, as I said, the question is big, because water-related disasters are the most impactful climate-related events. And here you see in a picture related to 2022. So this is the cost of the disasters that have been occurred in 2022, divided by categories. And of course, these costs are estimated. So it's there was a big cost associated to the Hurricane Ian, and then there was a drought in Europe in 2022, you may remember it, and then some floods in China, a drought in China, and then you see the costs associated. And indeed, these are all disasters associated to water, so the question is relevant. And of course, a good question is, but if we look at the data, what do we see? So if we look at the data, the progress of the data in time, what do we see? And here you see this question, in your opinion, is the frequency of floods increased at the global level? And the answer are yes, it is increased, yes, it is increased, but it is still not clear. No, it's not increased, yes, it is increased for the effect of land use change. All of these questions are relevant and possible. Actually, you can understand what is the correct answer because I already made an introduction. Yes, it is increased, but it is still not clear. Okay, what the drivers are and what is the relative contribution. But there is to say that the picture it's not so clear because first here I am talking about the frequency of floods. So if you look at the data on the flood frequency, the situation is not so clear. If we look at the flood damages, there is a clear increase in time. And so you may conclude that if the damage is increased, it means that the number of floods is increased. But actually, the damage is also increased because it is the value of the flooded areas that is increased, what we call exposure in technical terms. Of course, if you're flooded in an area that has no value, you don't have any damage. So it's different, a different story, talking about damage and talking about flood frequency. It's a different story. So the damage is increased. But if we look at the frequency of floods, the picture is not so clear. So for instance, in Europe, if we look at big floods, I mean, big means floods that occur for overflowing of large rivers. In Italy, I say large is not a proper terminology, but I would classify as large rivers the Po, the Tevere, the Arno, and few else, few more. So if we look at these big rivers, and if we look at the trend in flood frequency in Europe, in Italy, they went down in terms of frequency. So after the Po River flood in 2000, we didn't have any major flood in Italy. In Europe, the situation in the north of Europe, we notice an increase, which is probably due to the contribution of snow. In Central Europe, it is more or less stable. I'm talking about flood frequency. And in any case, where you find an increase of flood frequency, we should also take into account land use change, which is a very relevant driver. In fact, land use change is blamed several times as the main cause for a flood. So the answer to the question, indeed, it's not so easy if one doesn't have any additional information, because one may also say, yes, it is increased by the effect of land use change. Actually, this is not always clear. So basically, the correct answer is that one. And here you see a comment, flood frequency is increasing for the combined effect of different anthropogenic impacts. Climate change and land use change are the most important drivers. Their relative contribution varies depending on the local picture. And keep in mind that when you talk about climate change, it's a global problem, but the implication climate change is a local problem. And therefore, the local picture is extremely important. You may say the implication is not always local because global warming, yeah, indeed, global warming is global, but the implication, when I talk on the impact on people, it's an impact, it's a local impact. Local conditions play a relevant role. Okay. 1 second. So what is uncertainty? This is interesting because I started talking uncertainty and we have a clear idea of what is uncertainty. I mean, uncertainty means that I have to take a decision and I'm not sure what decision should I take. But on the other hand, if we talk about science, we have to work with definitions. Definitions are extremely important. I think I already mentioned on Monday, I said, sorry, I stick on definitions, but definitions are important. Why they are important? Because we need to communicate with people, and if we use different terms or we use the same term with different meanings, communication doesn't work. So we need definitions to talk among scientists, to talk among technicians, and for the scientists to talk with technicians, we need definitions. So how can we define uncertainty? There are several definitions that can be used. In environmental sciences and in statistics, I would say that I would define uncertainty as lack of predictability. So if I had to choose among the following statements, what best describe my idea of uncertainty in science, I would select the first one. Means limited predictability. And I also would say that it does not necessarily mean lack of knowledge. There are some processes that we know perfectly. We could describe them perfectly with a numerical model, but they are uncertain. And the classical example is tossing a coin. Everything is known there. The physics is perfectly known. The theory is perfectly known. But we cannot make any prediction of the outcome from tossing a coin. We can also say that half and half, it can be head or tail, with the same probability. This is what we can say, which is very good. It is very good indeed, because we know that we have a probability of 50% of getting the right answer. It is very good. It is very helpful. It clarifies why uncertainty is useful, even for tossing a coin. But we cannot absolutely make a precise or deterministic prediction. Absolutely. By the way, tossing a coin, what I said, my comment about tossing a coin may seem trivial, okay? Like 50% probability of getting a tail, 50% probability of getting an head. You may say, it's a stupid statement, it's clear. We know everything of it. Let me tell you that a famous statistician, Pearson, in it was in the 18th century, he wanted to prove that he was correct, that the estimate of probability of tossing a coin was correct. And what he did was, this is really nice to say, he tossed the coin 24,000 times. It doesn't take much time. I think in 1 week one can do that. And he got 12,000 plus 24 heads. And then he said, look, you see that the theory is correct. It is not so easy, because if you make several experiments, then you can demonstrate it. But if you toss the coin just 2 times, you can get 2 heads very easily. And therefore, to demonstrate with data what is your conjecture, theoretical conjecture, wouldn't be so easy. So in climate, you have data for the corresponding equivalent of 2 tossing a coin, 2 tossings. And therefore, it's not so easy to prove with data what is your understanding of probability. So when I say probably humans are responsible, at least in part, but in what percentage, we have no data. We have to rely on models. Okay, so uncertainty, I would say that means limited predictability, lack of predictability. It is not necessarily due to lack of knowledge. Tossing a coin, we know everything, but it is completely unpredictable. Uncertainty may be also caused by imprecise information. This is not really something that we can exclude, but if I say may, if I say is caused, it's not correct answer, because it's not only caused by imprecise information. It can be caused by several factors, and uncertainty may be caused by imprecise model, imprecise theory, imprecise data, because models have to be, in many cases, we need to tune them with data. And imprecise initial conditions. Do you know the butterfly effect? Okay. Most of you have heard about the butterfly effect. If not, look on Wikipedia. Butterfly effect means Lawrence, I think. Yeah, Lawrence said that a butterfly flipping in Japan may cause an hurricane in New York. This means that a small change in the initial condition of a system may turn out in a completely different result at the end of the story. And indeed, this is a typical effect that occurs with turbulent systems. When there is turbulence, you can just vary the initial condition of a small amount, and the final result is an hurricane. Indeed, it is true. In principle, it is true that a butterfly flipping in a butterfly flying in Japan may cause an hurricane in New York, because it's the effect of chaos, of turbulence. And this effect of the initial condition cannot be eliminated. So this means that even if we were able to measure the initial condition with a high precision, still we have a lot of uncertainty, because we cannot predict the final outcome. Everything is clear so far? Okay. This subject is meant to be directed to students with different backgrounds. So even one person that has something not clear, please let us know, because it can be the opportunity to start a discussion. It's very nice if we could engage in some discussion. And you can challenge me also. I appreciate it. If you don't agree, if you think I am not clear, just let me know. And here I think uncertainty indeed means limited predictability. Even if the knowledge of the process is perfect, tossing a coin is an example. Think of tossing a coin, okay? Now, let's also define what is science, because the title of the subject is Science of Climate Change. In the introduction, we have to talk defining science. So science is a systematic effort that builds and organizes knowledge in the form of testable. I go back to my initial discussion on medicine, testable explanations and predictions about the universe. When we make a prediction, we should be able to say uncertainty. The term testable is essential. Science is objective, and its conclusions should be supported by testing and validation. And let me add, it's not added here, the conclusion, the experiments should be repeatable by everybody. Today, there is a lot of support to science, open science, to reproducible science, and which means also to make the data and any software available to the readers, to the scientific community. This is a dramatic change with respect to the past. When I started my career 25 years ago, say almost 30, unfortunately, but as a professor, I started 25 years ago. There were some of my advisors that said, always recommended me not to make the data available and not to make the software available for two reasons. First, because collecting data was indeed a huge effort, and therefore researchers were a bit protective against their effort. They wanted to take the full credit for it, which is fair, I mean. But the result was that there was a resistance against sharing data. Also, some of the data were made available by governments, military services, with the obligation not to share them. And also, my advisors were not happy to share the software for the same reason, but also for the reason that, science is competitive and science may be subjected to mistakes. Reproducibility may allow other people to demonstrate that I was wrong, that I made mistakes. And this was, people were really scared by that. And therefore, this was a second reason for recommending not to share the software. Today, we cannot publish any scientific paper if we don't make the data available or if we don't provide a reasonable justification. There might be a justification for keeping the data secret, like privacy reasons. If the data research is about people, some of the data are protected by privacy. But if there are these limitations, then we are required to declare them. And in most of the cases, we are also required to make sure that the result is reproducible. And therefore, also, we are requested to make the software available. I think this has been a big progress. And of course, somebody may demonstrate that we made mistakes, but then what's the problem? As scientists, we are allowed to do that. We are allowed to make mistakes. As engineers, not. But as scientists, we are allowed to. What we are not allowed to is to make fraud. But if the mistake is a genuine mistake, there were several mistakes in science, it's fine, I mean. Otherwise, it wouldn't be science. Okay, here, second sentence, the interpretation of testing and validation may be, however, subjective, unfortunately. And therefore, the history of science is studied with erroneous conclusions. And an illustrative example is Aristotle's convincement that the Earth occupies the center of the universe. He was not the only one, by the way. Okay. So here you see a lot of a list of disciplines. They are all related to climate science, actually. If I had to identify what is the most related, I am biased here. I would say hydrology, because it's the science of the water cycle. But all of them are related to climate science in different levels, with different levels of involvement, depending on the problem, but they are all involved. Okay, and this is, I think, the final slide. So this course last year was called Science of Climate Change and Science Actions. And then they made a mistake when they replicated the title for this year, and they forgot to say climate actions. But actually, we are also talking of climate actions, because of course, this is our first course. And why should we study science for? Okay, for speculative knowledge, but for the case of climate change, we also need actions. And this slide basically says what are the main questions, the main research questions associated to climate change. So the questions are those that you see here. This is not a complete list. It is a bit subjective, but so what is the magnitude of climate change? This is important that we know what we are talking about. And I have a motto which says, if you want to identify a solution to a problem, you have to know it. And knowing the magnitude is the first thing. How climate change is affecting water, socioeconomics, and public health? Of course, we know that there are concerns associated to climate change for water, for socioeconomic setting, and for public health. How is climate change affecting all of these? What are the causes of climate change? Because knowing the cause of a problem allows you to find a solution. How can we generate future climate scenarios? How can we predict the future climate? This is a big question. And the scientific literature is moving forward quickly in this direction. But still, there is uncertainty and not quantifiable uncertainty. This is a big issue. As I said last week, uncertainty is not a problem once we know it. If we cannot quantify uncertainty, it's a big issue. And finding solutions, we need predictions. No problem if the predictions are uncertain, but if they are, and they are for sure, then we should make an effort to quantify it. And then uncertainty of climate predictions. I anticipated my last question. Here I am observing, this is a lesson reading, if you want to get an idea of the impact of climate change and droughts, and I think an idea of a very simple analysis using open data. Actually, this very simple analysis using open data through the publication of Science Advances, which is an expected and reputable international scientific journal. And I think pointing out to this paper, which is, you can find it on Google, and it's available, it's open access. Everything is, almost everything is open today. It is an easy read. And it is also an example, as I said, of a very simple analysis based on open data. And what is the conclusion here? The conclusion is that indeed the drought risk for the Po River is increasing, not for the lack of rainfall, or let's say, not significantly for the lack of rainfall or a decreasing rainfall. The problem is anticipated snowmelt, also in this case. and therefore we get more flow in the spring season and less flow during summer. But unfortunately, we need water in summer because in the spring season we don't need to use water for irrigation. Okay. I have a question for you. You can think about it and then you give me the answer maybe next week if I'm not providing the answer before, but I don't think we will get there today. The question is, if you think about global water use by humans, or let me start with another question. You can easily find these replies by Googling, by the way. But try to make an effort before Googling to gain an idea of your expectation, because I think it is interesting. I'm not asking you to tell me after here today your expectation today, but if you want, you are much welcome, and I would encourage you to do so. So first question, do you know in the global amount of water that is on the earth, the percentage of the water that is fresh, meaning not salted, and if you know this percentage, tell us. Okay, so global amount of water in the Earth system. What is the percentage of water that is not salted? First question. Second question. If you think about the global water used by humans, in your opinion, what is the most important use of water? We can use water for several purposes, like drinking, or let's say civil use. Let's make a big category, civil use. Let's make three big categories. Civil use. Civil means everything is related to the tap water in your house. Everything that is given by water supply systems of potable, drinkable water. Potable, I'm not sure it is in English. It is an English word. Drinking water. This is one category. Second category, industrial use, not necessarily drinking water. Some industries use drinking water, I mean water from the public water supply system, but most of them use their own aqueducts and they use water of lower quality. But let's call it industrial use to mean all the water that is used by the industry. Okay, there is a small intersection with the civil use, but let's assume that they are separate. Third use, irrigation. Okay, so if you had to say what is the most important one, and another more detailed question would be, try to make a guess of these percentages. So first question, there is one, mind you, willing to give a reply. So what is the percentage of fresh water with respect to the total? Yeah, say. Sorry. Okay. He said between 2 and 3%. Somebody's agreeing or you agree? Less. You would say less. Less. So you mean less than 2-3%. Everybody? That's okay. Actually, she's right. It's 3%. Okay, but not all of this 3% is usable because part is ice, like polar ice, or so. If you look at the part of it that is usable, is much lower. It's 1%. But in terms of not salted, it's 3%. Okay, good. This was quite easy, by the way. So, what is the most important use between civil, industrial, and agriculture? What is your guess? Sorry? Industrial, okay. So, any other opinion?
I have a question. In this division, where is the food industry in the
Okay.
irrigation and like the meat industry?
This is a nice question. So she asked, where is the food industry located here? In the irrigation or industrial use? Okay. Conventionally, the food industry is in irrigation. So food production is irrigation. Okay, food elaboration, let's say food preparation is in the industrial sector and also part in the civil sector. But usually the food requirement for water is placed in irrigation. So do you have a reply at this stage?
I'm saying
You would say irrigation, okay? And somebody agrees or? And if you say irrigation, which is the correct answer, by the way, so it's irrigation, but in what percentage with respect to the total? Okay, she doesn't know. Yeah, it is 70%. So industrial use is 15%, and the civil use is about 25%. And in Italy, more or less, the percentage is the same, a little bit less for irrigation, 60%. But let's say that mid-latitude is about 70%. 70% is the global. So this means that water resources problems are water for food problems, not water for people. By the way, the civil use has the priority in most, I would say, all of, but not really, I don't want to make mistakes, so I would say most of the countries, Italy for sure. So priority. So if you get a drought, the first thing to shut down is irrigation, and then industrial and civil. But let's say the last one is civil, and the first one, it depends the context. It depends on decisions taken by the government. So if we experience a shortage, where to start with the cuts depends on the decision of the government, which usually uses crisis units to take the decision. But for sure, the law says that civil use is the last one. Okay. And but I mean, the big problem is water for food, and therefore climate change and the fact indeed on water availability in certain regions, and the fact is on water for food. Okay. I think we are done here. Okay, we are done indeed. Now, next one is a more detailed discussion on climate change. And let me just see if I have the PowerPoint here. I'm not sure. Yes. Okay. This is just a summary, so I go to the next one. Okay, so what is the purpose of this lecture? Is to discuss in deeper detail what are the effects of climate change, discussing the effect on the single variables. So far, we only talked about temperature. Now I want to say something more. And so I will make reference to this PowerPoint in order to get a summary of what I'm saying on the screen. But remember that your reference for studying is, is this lecture here, okay? And in particular here, I have some figures that I will highlight. Okay. Before starting, given that we are starting a new lecture, I think we can make the break now. If we give us 15 minutes of break, okay? And I am cutting off video and micro, and the video will continue moving forward, okay? Okay. We can restart. So as I said, now we start with the second link in the list of lecture notes in my website. And the purpose of this second lecture is, as I said, to get in deeper detail into the quantification of climate change, and not only for temperature, but also for other variables. There will be some very slight repetition from my introduction, but the purpose of this lecture is indeed to try to gain a better understanding of what climate change means and climate change implications and also climate change drivers. So it's basically something more and something more detailed with respect at what I just introduced. So first of all, we have to be aware that climate change is not a long recognized problem. What I mean to say is that we recognized climate change as a problem only a few decades ago, about 30 years ago, because it was the onset of global warming. And global warming, the term refers to the recent increase of temperature, so global warming is relatively recent. If you remember the graph of global temperature that I showed you before, global warming started, the increase of temperature started about in the beginning of the 90s, so 35 years ago, more or less. And therefore, it was about 30 years ago that the scientific community started to be concerned about climate change. The concern about climate change is strictly related to the concern on sustainability. The concern on sustainability of human development, which became indeed a concern for the global humanity a bit earlier than the concern of climate change. Sustainability is a concept that was first discussed around 1970, end of 1968, start of the 1970s. And the concern was originated by the huge development. You may remember that we talked about great acceleration, the huge development of human activities that was associated with the so-called economic boom. So the recovery after the Second World War. After the Second World War, there was a massive investment on recovery. It was an international investment, an international joint effort of several countries who put a lot of money, who got also publicly indebted with people in order to promote a quick and very effective recovery after the war. And this originated the so-called economic boom, which promoted a huge expansion of the human activities. But quite soon, we realized that there were implications on environmental sustainability. So in 1968, for instance, in Europe, it was promoted the European Charter of Water, which is a series of recommendations in order to make sure that our use of fresh water was sustainable. And it was written in 1968, approved in 1968, which means that before that in Europe, water was not really a concern. But with the increase of the welfare, the increase of cities, the urban expansion, of course, water became a concern. And then already in the 1970s, people got concerned about sustainability. And sustainability means, according to a definition that was proposed precisely around 1970, sustainability is meant to be the fact that we can reassure the future generation that they will have the same opportunities in terms of also of exploitation of natural resources of what we are having now. Now, there are several variables which, and the progress trends in several variables that originated the concern on sustainability and then later on climate change. And here in this slide, you can see some of them, but we don't need to go into the real details. On the upper right, you see a water balance for the Po River, which it is under attention because the Po River provides water for irrigation to a large part of north of Italy, and also provides water for civil use to a large part of north of Italy. And here in the bottom, middle bottom, you can see graph of the annual minima of the Po River water level from 1920 to 2009. You see that there is a slight increasing trend. It's not statistically significant, by the way, but it is there is a slight decline, which is due most probably to the increased water withdrawal for irrigation after agricultural expansion. Glacier retreat is another variable, and this is a picture of an artificial reservoir. You see the water level that for some reservoirs is decreasing. Here I'm not listing the estimates on groundwater storage. Groundwater storage is also another concern because groundwater takes a long time in order to be recovered. And therefore, if we exaggerate with water exploitation, of course, we run the risk of running out of water. And groundwater is indeed something relevant because in most of the countries, at least in the Western world, is the main provider for drinking water. So let's try to look then in more details. First of all, here you can see some of developments associated to the great acceleration, which are concerning. Some of them are trivial, others are less trivial, but the list could be longer. So first of all, intensive agriculture is a matter of concern. Remember that agriculture has a high contribution to CO2 emissions. We will see the details of estimated emissions, human emissions, and the relative contribution of activities. The most important ones are energy production and intensive agriculture, and agriculture, not intensive, sorry, agriculture, broadly speaking. And energy production is really a concern. If I well remember, but we will see the numbers, is responsible for 70% of the human emissions. And, you know, energy production is also related to use of electric cars, of use of electric facilities, like, for instance, heating the buildings. Now there is a shift towards electricity. The problem is that if we want to be effective on reduction of emissions, this progress towards use of electricity should be associated to a progress in clean energy production. And clean energy production, if we want to go beyond lip service, it is challenging because, I mean, the reliable sources for energy productions are emission expensive. So if we look at the renewables, most of the renewables are not reliable in terms of modularity, in terms of the possibility to tune, to regulate them. So wind power, we have wind power when there is wind. Solar power, we have solar power when there is a lot of irradiation, of solar irradiation. And keep in mind that energy cannot be stored, or it can be stored only in a very limited quantity. So energy cannot be, in a way, put into a deposit. energy, once it is produced, has to be used. And therefore, the opportunity of regulating energy production is extremely important for an efficient use of energy. But these opportunities are limited and given by energy productions that are emission expensive. So it is indeed a challenge when we talk about decarbonization. It is not just enough to use anything electric. Also, when we talk about clean energy production like hydroelectricity, it's clean. But still, we don't have to forget that the construction of dams, the construction of river barrages is emission expensive. And the maintenance of these infrastructures requires emissions. So strictly speaking, it is problematic to identify a really clean solution for producing energy. And our energy demands are continuously increasing. So perhaps we have to think about reducing our energy demands rather than incrementing them. But on the other hand, reducing the energy demands means that we have to step a little bit back in our development, because our current development is really energy demanding. If we look at the carbon dioxide concentration in the atmosphere, it is indeed increasing a lot. And there was a market increase during I showed you the numbers, during the past century. And such increase is probably due in large part to humans. It is still not very clear because the carbon cycle, the carbon cycle is another complex system. And the carbon cycle is regulated by the so-called carbon storages, which are the deposits of carbon into the Earth system. So fossil fuels are a deposit of carbon. And these deposits originated, we know, in geological times with the decomposition of organic matter. So basically, the mechanism is that forests and living species have a potential to absorb carbon. And then this carbon, after the death of forests, death of trees, is incorporated into the body of the Earth in different forms. And one of the forms is through oil. It is a process that requires a lot of time. In fact, one solution that is proposed for decarbonization, for reducing the CO2 concentration in the atmosphere, is the injection of CO2 into the body of the Earth in order to accelerate this process. The oceans are another carbon sink, so storage of CO2. They absorb a lot of CO2 depending on the ocean temperature. In particular, when the temperature of the ocean decreases, then the capability of the ocean to store CO2 increases. Conversely, with an increase of the temperature of ocean, there is a massive release of carbon, of CO2 by the oceans. So you see that CO2 concentration in the atmosphere and temperature, global temperature, are related processes, which means that if for some reason you increase, perhaps with a natural process, the global temperature, and in fact in the past, we know that in geological times, in past eras, we had a much higher temperature over the Earth. I already told you that we are in a glaciation now, during a glaciation, and the glaciation is marked by the presence of ice caps. In the very far past, in geological times, we had periods without any glacier at the caps. The temperatures was larger, was higher, and the CO2 concentration was much higher than today because the two things are related. Also with the natural process. So it is a debated question now, strong debate. Who comes first? Comes first the increase of temperature or the increase of CO2? And the two things are related, as I said. So you see the complexity of the mechanism is relevant. There is a lot to learn and know. Okay, we already defined weather and climate, so this is an overlap. Let's forget about it. And it is interesting to look at the picture on the right. What is the picture on the right? Is the increase of temperature in selected cities from during the past century, more or less. And you see that when you look at the temperature in cities, the temperature increased more. Why? Because of the urban expansion. Let me show you another figure. Okay, the other figure that I wanted to show you is this one. So this is a graphical representation of the so-called heat island effect. So in the cities, you have a higher temperature than in the surroundings. This is a relatively recent phenomena because it was experienced during after the Second World War with the urban expansion and the proliferation of home heating. In the past, we didn't use much to heat our homes like today. Today, we are looking for higher and higher temperatures because we want to feel comfortable. But this, of course, originated a higher temperature inside the cities. This is one of the reasons. Another reason is that urbanization causes a local greenhouse effect. And the solar irradiation is less absorbed by the soil with respect to the green environment. In fact, one solution proposed for mitigating the urban heat island effect is to increase the green surface into the cities. You see on the figure that they are trying here to increase the green surfaces, and in some cases they are also using green roofs and green walls. You may have heard of the green buildings that are completely covered by, like urban forests, that are completely covered by vegetation. It's a possible solution. There are several limitations of this solution. First of all, the durability, because the vegetation around buildings, of course, it's compromises the durability of the streets, of the paved roads, buildings. And another potential problem is the maintenance of these green areas, and especially if we are talking about green roofs, green walls, the maintenance is really demanding. But these solutions are intended to mitigate the heat island effect. By the way, this is an effect that is indeed responsible for heat waves in urban areas. Remember that, once again, a change is impactful when there are people there. So the urban areas are by definition vulnerable because there are a lot of people in there. And if you consider that in urban areas, the increase of temperature corresponding to a global average of 2 degrees of 1.5 today, it means that in an urban area, maybe twice that. And if you look at the graph here, you see that, for instance, in Tokyo, they went from, during the past century, from like 21.5 to 24.5. So it's 3 degrees. And 3 degrees for people that are not protected against it may be very impactful on public health. And the protection is air conditioning, which is in turn contributing to increase the temperature in the urban environment, because it's also the proliferation of air conditioning that causes the 8 island effect. So this is a case where we are talking about temperature, but we need to focus on the temperature where people are located. And here you see a reference to a paper that was published precisely on this problem. And this paper demonstrated that indeed there has been in some cities an increase of temperature in Australia, for instance, and Eurasia, of more than 0.6 per decade, which means that in 50 years is more or less 3 degrees, as I said. And there are some cities which experienced a larger trend than that, like Houston, Moscow. They experienced a larger trend, more than 0.6 degree per decade. So it is indeed something that needs to be taken into account and highlights the emergence of climate change, indeed, in an urban environment, which is for sure, in this case, human-induced, maybe not due to global increase of emissions. So it is a case where even if we were able to mitigate climate change at the global level, the implication in the urban environment would remain there. So the solutions have to be very targeted. Now, let's start talking about the forcings of climate change. So what are the forcings? Forcings are the drivers of climate dynamics. You can think of the forcing as the input variables of your prediction, of what determines, you can think of what determines the dynamics of a system. So for the case of the climate system, what is a forcing, what is a driver? It's solar irradiance. Solar irradiance is the fuel of the Earth system, is the fuel of any ecosystem, of any living, of any process related to the living bodies. So solar irradiance is the fuel of energy to the Earth system. So we get our energy from the sun. And even when we believe that our energy is produced in a different way. So you may think of, for instance, burning fossil fuels. This is energy that doesn't come from the sun, maybe we think. Rather, it comes from the sun, because I just said that fossil fuels come from organic matter that grew up using solar energy. So this organic matter, these fossil fuels, are a storage of past solar energy. So if fossil fuels formed, is because in the past there was a living system, a living body, vegetation, that absorbed solar energy and transformed it into the fossil fuel. Another form of energy, which you may think is not related to the sun, hydroelectricity, hydropower, is related to the sun because the water cycle is fed by the solar energy. If you get water up on the mountains, if water gets from the ocean through evaporation up to the mountains and then in artificial reservoir, is for the solar energy. The energy for moving the water from the ocean to the top of the mountains is solar energy. So the sun is our fuel. By the way, you know that the duration of the sun is not unlimited. There will be one day, finally, a decline in solar energy. There will be one day, finally, a decline of the temperature of the core of the Earth. And a decline of the temperature of the core of the Earth will mean that the magnetic field will disappear. Without magnetic field, it's not possible the life over the Earth. because the magnetic field is acting like a screen against the direct radiation of the sun. So there will be one day when the Earth system will die, like it happened over Mars. Today we know that over Mars there was a water cycle, there was water, a lot of water, there was an atmosphere, there was a water cycle. Maybe there was also life, we still don't know, but for sure there was water. And then the water disappeared. Why? Because probably it was a similar process. The core of the planet, because Mars is older than the Earth, the core of the planet cooled down, no magnetic system, and then direct solar radiation and the disintegration of the molecules of water. Just to be clear that we are not talking in any case of something that has an infinite duration. It's something that has a finite duration. Of course, for our time scale, is like infinite duration, because if it is billions and billions of years, of course, for our time scale, it's just to make clear that there is a natural process that is naturally evolving in a way that we now can understand. And of course, we have to make sure that we are not accelerating this evolution. So how we define solar irradiance? It's the power per unit area, surface power density, received from the sun. And solar irradiance is measured in watts per square meter. And this is a bit variable because the sun has a 11-year sunspot cycle, as we know, which means that the solar irradiance is varying with a cycle of about 11 years. And measurements of solar irradiance are affected by uncertainty, especially those going back to the far past. And we have global maps available by the Global Solar Atlas. And here we can find, I don't know why there is a potential security problem. One second, because it's a Wikipedia page and don't understand why it's giving a potential security problem. Okay. So this is a Wikipedia page for the Global Solar Atlas. And here, these maps are very useful for producing solar energy, for renewable energy. And because they show the potential in terms of solar energy production, so clean energy production by the different countries. And here you can see all the data that you need if you are interested in this data, of course. Okay. Oops, sorry. Again, greenhouse gases, it's another driver of climate dynamics. Greenhouse gases are responsible for the greenhouse effect. I don't think we need to focus on what is the greenhouse effect. It is the effect that is consequent to increase of concentration of greenhouse gases in the atmosphere. CO2 is the most important, but it's not the only one. There is also methane as a greenhouse gas. There is water vapor. Water vapor is a greenhouse gas. And you understand, for instance, that when there is a lot of humidity in the atmosphere, the temperature is increasing. We know that in clear days, the temperature is colder than in foggy days, for instance. And this is due to the action of the water vapor as a greenhouse gas. And the greenhouse basically is reflecting the back emission of solar irradiance from the Earth. So we have the energy from the sun. The energy from the sun hits the Earth, and part of it is reflected. And then the reflected part, if there is a high concentration of greenhouse gases, is kept into the proximity of the Earth's surface. And therefore, there is an heating of the atmosphere. Greenhouse gases, we already talked about concentrations, CO2 emissions, sorry, CO2 concentration and emission. So here, there is an interesting graph. This is showing, is taken from our boarding data. It is showing the CO2 emissions per capita, the vertical axis, against the gross domestic product per capita in the countries. And so China, United States, the size of the point is proportional to the population of the country. So what you can see is that there is a clear trend. Increasing gross domestic product means increasing of per capita emissions. This is perfectly understandable and fine, but this means that, at least according to this picture, reducing the emissions in the present socioeconomic settings means reducing the GDP. Of course, if we want to reach the double target of reducing emissions without reducing the GDP, we need a change of the current organization, of the current societal organization. Not sure this is possible. Of course, we want to make it possible, but making it possible means finding solutions. Okay, now emissions, look at the graph here. These are greenhouse gas emissions, dark line here, from 1990 to 2015, more or less. Yeah, I think this graph is dated 2015. And then we turn into predictions. According to different scenarios, this is a new information that I am introducing. If we want to make a prediction of future climate through climate models, we need prediction of concentration, future concentration of greenhouse gases. Remember, making prediction is always difficult, especially when they refer to the future. This is a famous say. A famous quote. I don't remember who was the first saying this, and of course, it's a lot of fun. But making prediction of a future human emission means making assumption on how we change our societal system into the future. Because, of course, if we commit to reducing them, it depends on how successful we will be in doing this. So this means that we need to introduce different scenarios. We have to make assumptions on the level of success in reducing the emissions. And for each assumption, we try to make an estimation. So the first assumption is what is called business as usual. So no climate policies. We just continue the trend, we just continue to burn fossil fuels as we are used to do. And this is the worst scenario, no climate policies. With an uncertainty band. With an uncertainty band estimated by using different prediction models, different societal prediction models. We need to make a prediction on our future development. For instance, the human population will continue to increase, or at a certain point we will reach for naturally a cap. This is possible because, of course, we cannot think of human population increasing forever. There must be a limit. We know that for all the living species, when they are placed into a given environment, there is a sustainable population density. If it is exceeded, a natural selection introduces a limit. This is understandable. And in the Earth system, we don't have resources for everybody. So it's possible that at a certain point, we will reach a limit. And how we will reach it, it's a big question. It's an interesting question. But in any case, whatever is the solution that we find to make our future sustainable, it's clear that there is a limitation. So, of course, the business as usual scenario will make different prediction on future population, and then there is a certain demand. So different prediction models are used to determine this uncertain demand. And then there are other scenarios. There is another scenarios called current policies, and look, these scenarios are also termed with acronyms. You may hear something like SSP 8.5. These acronyms are recently changed. I'm not introducing them now. I prefer to use a textual definition to define them by words. So current policies means in 2015, we have already started to activate solutions for reducing our emissions. And this is called the current policy scenario, which predicts that we will reach a cap of CO2 emissions in 2050. Actually, some scientists made a recent contribution. They are convinced that we already reached the top, the cap, or we are very close. And this is current policies. And then there is another scenario that is corresponding to meeting future target of max global temperature increase. So this is the scenario for the target 2.4, which means max 2.4 of increase of global temperature with respect to 1850. And then the last one is the 1.5 pathway. The 1.5 target was fixed by the Paris Agreement in 2015 or 2014, no, 2015, I think. The Paris Agreement was an agreement between international head of states, which agreed to fix this target, to make efforts to meet this target. It's clear that it was clear already a couple of years later that it was difficult to attain it, because indeed it required a massive effort in terms of decarbonization, which the countries couldn't meet because for lack of funding, lack of resources. So these are the future emission scenarios, and they are, of course, a fundamental driver. So when you hear about predictions of future climate scenarios, you will also listen to people mentioning the emission scenario that supported this prediction. There is a general convincement that the business as usual is too conservative, is too pessimistic, is too precautionary. So today people tend to rely on the current policies, but actually it depends also on the decision of the individual researchers. Some researchers still prefer to stick on the business as usual. Needless to say, you see that there is uncertainty associated to these predictions, and needless to say, the uncertainty is also related to human decisions, to societal development. And this is a big issue because, to make predictions, for instance, on the future geopolitical asset, it's impossible even at a small lead time. And because it depends on individual events like the outcome from an election. You have seen what difference can be made by the outcome of the election, and even in relatively small countries. And therefore, making this prediction is indeed problematic. Also, here there is a mention on the relevant call of clouds. Clouds is water vapor, so I already mentioned that this is extremely important. But on the other hand, it gives to me the opportunity to talk about feedbacks. So a change in a given system originates a feedback. What is the feedback? The feedback is the reaction of the system to the change. So, for instance, if we feel cold, if we feel that the air is too cool for us, our feedback is to put some additional clothes on. And for instance, nature, when there is a shock in the system, reacts with actions that try to compensate this shock. This by definition, because the living systems are resilient by definition. Nature is resilient by definition, otherwise it wouldn't resist, as I mentioned already last week. So if nature exists, it's because it is able to recover after a shock, to react. And this reaction is the feedback. And why feedback is important? Because the feedback usually tends to compensate a change, to mitigate a change, to make sure that after a change there is a conservation of the equilibrium. But there might be some cases where the feedback is reinforcing the shock. And this is our concern. So try to understand the feedback of the climate system to increase the CO2 concentration, increase temperature, and understand whether this may reinforce the perturbation or mitigate the perturbation. Here is an example, clouds. If you have an increased temperature, global warming, we should have increased evaporation. Increased evaporation means more water vapor, more clouds, but the clouds are acting as a screen on the solar irradiance. They may act as a screen. And therefore, even if the clouds tend to increase the greenhouse effect, but they, on the other hand, are also reflecting part of the solar irradiance. And therefore, the increased evaporation may compensate global warming. This is an example of a feedback that tends to mitigate the shock. On the other hand, if you think at the oceans, let's suppose that we have an increase of CO2 caused by humans, which causes a greenhouse effect, an increase of temperature. Then the increased temperature means increase the temperature of the ocean and a higher release of CO2 from the ocean, which may reinforce the perturbation. This is an example of a feedback that may increase the shock. Problem is that we still don't know these feedbacks in the climate system. We cannot characterize them. Climate models reflect our current knowledge, but our current knowledge may be affected by gaps. And therefore, you understand another reason of uncertainty. Very often, if you listen to climate change, to discussions on climate change, people discuss about the feedback. So, for instance, in the case of clouds, I started by saying, increased temperature means increased evaporation. Actually, there were recent contributions by the scientific literature based on a lot of measurements of evaporation from liquid surfaces all around the globe, and we don't see an increase in evaporation. This is called, if you are interested in, it's called evaporation paradox. Okay. And we still don't know why. We believe that it's probably the fact that global warming has reduced the average speed of winds. evaporation is related also to wind velocity. With higher wind velocity, we have higher evaporation. So probably evaporation is not increased because of a reduction of the wind velocity. We are still not sure about that. So understanding the forcing and the feedbacks is an essential step. So far, you may say, okay, you are talking to us and you are listing a lot of problems. What is the train of thought here? Okay, I will also talk about solutions. But first of all, I wanted to start by trying to provide you with a knowledge of the complexity of the system and therefore a knowledge of a list of problems. I will stop here for today. Do you have any question? Everything is fine? Okay, I will make the video available and we see each other again next Monday. Thanks. Ciao.